I want to talk to you about quantum mechanics, not the popular version, not the mystical interpretation, not the philosophical debates about what it all means. I want to tell you what quantum mechanics actually says about nature and why it works the way it does. This is going to require some serious thinking on your part, because quantum mechanics is genuinely strange. Not strange because physicists made it complicated, but strange because nature herself is strange at the atomic scale. Let me start with a question that will guide everything we discuss. How does an electron get from point A to point B? In classical physics, the answer seems obvious. The electron follows a path. It has a definite position at every moment in time. You could, in principle, track it continuously from A to B. But this obvious answer is wrong, completely wrong, and the way nature actually works is far more interesting. Before we get to electrons, let me tell you about light. In the early 1800s, Thomas Young did a famous experiment. He shined light through two narrow slits onto a screen. If light were simply particles, little bullets flying through space, you'd expect to see two bright bands on the screen, one behind each slit. But that's not what Young saw. He saw multiple bands, an interference pattern, bright bands alternating with dark bands. This is exactly what you'd expect if light were a wave. Waves from the two slits overlap and interfere. Where the waves arrive in phase crest meeting crest, you get constructive interference, a bright band. Where they arrive out of phase, crest meeting trough, you get destructive interference, a dark band. So light must be a wave. Case closed, right? Not quite. In 1905, Einstein showed that light also behaves like particles. When light hits a metal surface, it can knock electrons loose, the photoelectric effect. But here's the crucial observation. The energy of the ejected electrons depends on the frequency of the light, not its intensity. Bright light and dim light of the same color produce electrons with the same energy. The only difference is how many electrons get knocked loose. This makes no sense if light is just a wave. A wave's energy should depend on its amplitude, its brightness. But it makes perfect sense if light comes in discrete packets, particles we now call photons. Each photon has energy equal to Planck's constant times the frequency. A dim beam of light just means fewer photons per second, but each photon still carries the same energy. So which is it? Is light a wave or a particle? The answer is neither and both. Light exhibits wave behavior in some experiments and particle behavior in others. This isn't a defect in our understanding. This is how nature actually is. We're forced to use two different classical concepts, wave and particle, to describe a single quantum entity. Neither concept alone is adequate. Now let's go back to Young's double-slit experiment, but with a twist. Instead of shining a bright beam of light, let's send photons through one at a time. So weak that only one photon exists in the apparatus at any given moment. What happens? You might think that each photon goes through one slit or the other, and we'd see just two bands on the screen. But we don't. We still see the interference pattern. It builds up gradually, one photon at a time, each making a single dot on the screen. But after many photons, the pattern of dots forms the same interference bands we saw before. Think about what this means. Each photon somehow interferes with itself. It doesn't go through the left slit or the right slit. It goes through both. That's the only way to explain the interference. A single photon explores both paths simultaneously and interferes with itself. This is not a metaphor. This is what the mathematics tells us must be happening. But here's where it gets stranger. Suppose we try to determine which slit the photon actually goes through. We set up detectors at each slit to see which one the photon passes through. The moment we do this, the interference pattern disappears. We see just two bands, as if the photon went through one slit or the other like a classical particle. The act of measurement changes the behavior of the system. This is not because our detectors disturb the photon, though that's a common misconception. The change is more fundamental than that. When we don't measure which slit the photon goes through, we must describe it mathematically as going through both slits. When we do measure which slit it goes through, we must describe it as going through only one slit. The mathematical description, what we call the quantum state, changes depending on what information is available. Now, the key insight. In quantum mechanics, we don't describe a particle by saying it has a definite position and momentum at every instant. Instead, we describe it by a probability amplitude, a complex number associated with every possible configuration the system could be in. For a particle moving from A to B, there's an amplitude for every possible path the particle could take. The straight path, a curved path, a wildly zigzagging path. Every conceivable trajectory has an amplitude dot. These amplitudes are not probabilities. They're complex numbers with magnitude and phase. To find the probability of detecting the particle at a particular location, you add up the amplitudes for all the ways the particle could get there. Then take the absolute square of that sum. This is crucial. You add the amplitudes first, then square to get probabilities. You don't add probabilities directly. This procedure, adding amplitudes then squaring, is what produces interference. Let me show you exactly how this works with the double-slit experiment. Call the amplitude for the photon to go through the left slit and reach point P on the screen, amplitude A. Call the amplitude for going through the right slit and reaching P, amplitude B. Both A and B are complex numbers. If only the left slit is open, the probability of reaching P is the absolute square of A, written as absolute value of A squared. If only the right slit is open, the probability is absolute value of B squared. But when both slits are open, the total amplitude is A plus B, and the probability is the absolute value of A plus B, all squared. Now, here's the key. The absolute value of A plus B squared is not equal to absolute value of A squared plus absolute value of B squared. When you square a sum of complex numbers, you get cross terms. These cross terms are the interference. They can be positive or negative, depending on the relative phase of A and B. At points where A and B have the same phase, the cross term is positive, constructive interference. A bright band, at points where they're out of phase, the cross term is negative, destructive interference. A dark band. This is why quantum mechanics is fundamentally different from classical probability. In classical probability, if there are two ways something can happen, you add the probabilities. In quantum mechanics, you add the amplitudes, and amplitudes can interfere. They can cancel each other out. Two possible ways of reaching the same final state can interfere destructively, making that final state less likely than if only one path were available. This never happens in classical physics. Let me give you the precise mathematical framework. Every physical system has a quantum state, which we represent as a vector in a complex vector space called Hilbert space. For a particle that could be in various positions, the state is a superposition, a sum of basis states corresponding to different positions, each with a complex coefficient. These coefficients are the probability amplitudes. When you measure the position of the particle, the quantum state collapses to one of the basis states and you get a definite result. The probability of each result is the absolute square of the corresponding amplitude. Before measurement, the particle doesn't have a definite position. It exists in a superposition of all possible positions. This isn't ignorance about where the particle really is. There is no fact of the matter about where it is until you measure it. This sounds mystical, but it's not. It's just how nature works, and we can verify it. The predictions of quantum mechanics have been tested to extraordinary precision, and they always work. The theory isn't vague or hand-wavy. It's completely mathematical and completely precise. Now let me tell you about a deeper way to think about quantum mechanics, one that makes the mathematics more intuitive. In classical mechanics, there's a principle called the principle of least action. To find how a particle moves from point A at time 1 to point B at time 2, you consider all possible paths. For each path, you calculate a quantity called the action, essentially the integral of kinetic energy minus potential energy along that path. The actual path the particle takes is the one where the action is stationary, usually a minimum. This principle is beautiful because it's global. Instead of tracking forces at every instant, you look at the whole path and find the one that minimizes the action. Newton's laws of motion follow from this principle. The trajectory you get, the path of least action, is exactly what Newton's equations predict. Here quotes sang the quantum mechanical version. To find the amplitude for a particle to go from A to B, you consider all possible paths, just like in classical mechanics. But instead of picking the path with minimum action, you assign each path an amplitude. The amplitude for a particular path is e to the I times the action of that path divided by h bar, where h bar is Planck's constant divided by 2 pi. Then you add up the amplitudes for all paths. The total amplitude is the sum over all paths of e to the I times action divided by h bar. This is called the path integral formulation of quantum mechanics. It's completely equivalent to the standard Schrödinger equation approach, but it gives you a different intuitive picture. What does this mean physically? Each path contributes an amplitude whose phase depends on the action of that path. Paths with very different actions have very different phases. Their amplitudes point in different directions in the complex plane. When you add them up, they tend to cancel out. Only paths near the classical path, the path where the action is stationary, contribute constructively. These neighboring paths have nearly the same action, so their phases are nearly the same, and their amplitudes add up instead of canceling. This is why classical mechanics emerges from quantum mechanics for large objects. For a macroscopic object, the action is enormous compared to h-bar. Paths even slightly different from the classical path have actions that differ by many times h-bar, so their phases are completely different, and they cancel out almost perfectly. Only the classical path survives. But for an electron or a photon, the action is comparable to h-bar. Many different paths have similar phases and contribute significantly. That's why quantum effects are visible. Let me make this concrete with an example. Consider an electron moving in empty space from point A to point B. Classically, it travels in a straight line at constant velocity. Quantum mechanically, it explores all possible paths, straight paths, curved paths, paths that loop back on themselves. But most of these paths have actions very different from the straight paths, so they interfere destructively and cancel out. The amplitude is dominated by paths near the straight line, which is why we observe approximately classical motion. But now suppose the electron passes through a region with a magnetic field. The magnetic field changes the action of different paths in a specific way, through the Aharonov-Bohm effect. Even if the electron travels through a region where the magnetic field is zero, the mere presence of the field in a nearby region affects the quantum amplitudes. This has been experimentally verified. It shows that the electromagnetic potential, not just the field, is physically real in quantum mechanics. Now there's something I need to address about measurement. People often say that measurement in quantum mechanics is mysterious, that consciousness plays a role, that the observer creates reality. This is nonsense. There's nothing mystical about measurement. A measurement is simply an interaction between the quantum system and a measuring apparatus that records information. Here, quote, S. What happens? Before measurement, the electron is in a superposition of states. The measuring device is also in a definite state, ready to measure. When they interact, the combined system evolves according to the Schrödinger equation. The result is an entangled state. If the electron is in state 1, the apparatus reads 1. If the electron is in state 2, the apparatus reads 2. The full quantum state is a superposition of these correlated states. From the perspective of the apparatus or anyone who reads it, the electron appears to be in a definite state. The interference terms between different measurement outcomes are still there in the full quantum state, but they're not accessible to any local observer. This is called decoherence. It's not mysterious, it's just what happens when quantum systems interact with large environments. The apparent randomness of quantum measurements, the fact that we can only predict probabilities, not definite outcomes, is built into the structure of the theory. It's not because we lack information, there are no hidden variables that determine the outcome ahead of time. Bell's theorem proves this. Experiments have confirmed it. The randomness is fundamental. Let me tell you about one of these experiments. In the 1980s, Alain Aspect performed experiments testing Bell's inequality using pairs of entangled photons. When two photons are created in certain ways, they can be entangled. Their polarizations are correlated, even though neither has a definite polarization until measured. According to quantum mechanics, if you measure the polarization of one photon along one axis, the other photon instantly has a definite polarization along that same axis, even if they're separated by a large distance. Einstein called this spooky action at a distance and thought it showed quantum mechanics was incomplete. He believed there must be hidden variables, predetermined values that both photons carry with them. Bell proved that any hidden variable theory must satisfy certain inequalities, relationships between the probabilities of different measurement outcomes. Quantum mechanics predicts violations of these inequalities. Aspect's experiments and many others since have confirmed the quantum predictions. The correlations are stronger than any hidden variable theory allows. Nature really does have this non-local character. Measuring one particle instantly affects the quantum state of a distant entangled particle. But and this is important, you can't use this to send information faster than light. The measurement outcomes at each location are random. You only see the correlation when you bring the results together and compare them. So causality is preserved. No paradoxes. Just quantum mechanics working exactly as the mathematics predicts. Now, let me address what quantum mechanics says about reality. Does an electron have a definite position before we measure it? The theory says no. The quantum state gives you the complete description of the electron. There's nothing else. If the quantum state is a superposition of different positions, the electron doesn't have a position. It's not that we don't know the position. It's that there is no position until you measure it. This troubles people. It troubled Einstein. He thought the quantum state must be incomplete, that there must be additional variables giving the electron a definite position at all times. But Bell's theorem and experimental tests show this is wrong. There are no hidden variables that restore classical definiteness. The quantum description is complete. What about Schrödinger's cat? This famous thought experiment involves a cat in a box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers and releases the poison, killing the cat. According to quantum mechanics, until you open the box, the atom is in a superposition of decayed and not decayed. Does this mean the cat is in a superposition of alive and dead? Technically, yes, but this is misleading. The cat is a macroscopic system with enormous numbers of particles interacting with their environment. Decoherence happens essentially instantaneously. The interference terms between alive and dead cat states are destroyed by interactions with air molecules, photons, everything in the box. From any practical perspective, the cat is either alive or dead, we just don't know which until we look. The superposition exists only in an abstract mathematical sense, not in any observable way. So what does quantum mechanics tell us about the nature of reality? It tells us that nature at the fundamental level is described by probability amplitudes, not definite classical properties. These amplitudes evolve according to precise mathematical laws, the Schrödinger equation, or equivalently, the path integral formulation. When we make measurements, we see definite outcomes, and the probability of each outcome is determined by the amplitude. This is very different from classical physics, where objects have definite properties whether we observe them or not. In quantum mechanics, many properties simply don't exist until measured. This isn't a limitation of our knowledge, it's how nature is. Asking where an electron is when you're not measuring it is like asking what the score of a baseball game is before the game is played. The question doesn't make sense, the property doesn't exist yet. But quantum mechanics is not arbitrary or mystical. It's a precise mathematical theory that makes definite, testable predictions. And every prediction that has been tested has been confirmed, often to extraordinary precision. The electron's magnetic moment has been calculated in quantum electrodynamics and measured experimentally, and they agree to better than 1 part in a trillion. This is the most precisely verified prediction in the history of science. The theory works. It works for atoms, molecules, solid-state physics, particle physics, quantum field theory. Every aspect of modern technology that involves semiconductors, lasers, MRI machines, GPS satellites, all of it depends on quantum mechanics. The theory isn't speculative, it's established fact. But here's what's truly remarkable. Despite its success, we still don't fully understand what quantum mechanics means. We can calculate anything we want to extraordinary precision, but the interpretation, what the theory tells us about the nature of reality, remains debated. The Copenhagen interpretation, the many worlds interpretation, pilot wave theory, consistent histories, these are different ways of thinking about what the mathematics represents. I've always thought these interpretational debates, while interesting, are somewhat beside the point. The theory tells us how to calculate, and the calculations work. That's what matters for physics. Philosophy is fine, but nature doesn't care about our philosophical preferences. Nature does what it does, and our job as physicists is to describe it accurately, not to make it conform to our intuitions. What we've learned from quantum mechanics is that our classical intuitions developed from everyday experience with macroscopic objects simply don't apply at the atomic scale. An electron is not a little ball. A photon is not a little bullet. These classical pictures fail. We're forced to use mathematics that goes beyond classical concepts, and we have to accept the predictions of that mathematics even when they seem strange. This is how physics progresses. We start with phenomena that can't be explained by existing theories. We develop new mathematics to describe the phenomena. We make predictions. We test them. If the predictions work, we accept the theory, even if it challenges our intuitions. Then we live with the theory, use it, explore its consequences, and gradually develop new intuitions. After working with quantum mechanics for decades, I've developed some quantum intuition. I can think in terms of amplitudes, superpositions, interference, It feels natural now. But I had to earn that intuition by working through calculations, understanding the mathematics deeply, seeing how it connects to experiments. There's no shortcut. You can't understand quantum mechanics just by reading popular accounts or thinking about philosophical interpretations. You have to do the calculations. That's my message. Quantum mechanics is strange, yes. It defies classical intuition. Absolutely. But it's not mystical or incomprehensible. It's a precise mathematical theory that describes nature with extraordinary accuracy. If you want to understand it, study the mathematics. Learn how to calculate amplitudes, how to use the Schrödinger equation, how to do perturbation theory. Work through examples. See how the theory predicts interference patterns, energy levels, scattering cross-sections, decay rates. The beauty of quantum mechanics isn't in vague philosophical statements about observers creating reality or consciousness collapsing wave functions. The beauty is in the mathematical structure itself, the way complex amplitudes combine to produce interference, the way the uncertainty principle emerges from the non-commutativity of operators, the way quantum field theory extends these ideas to describe particle creation and annihilation, giving us quantum electrodynamics, the standard model, our current understanding of fundamental physics. This is what quantum mechanics teaches us. Nature, at its deepest level, is mathematical. Not approximately mathematical, not described by mathematics, but actually mathematical in its fundamental character. The properties of particles aren't hidden away waiting to be discovered. They're created by the mathematical structure of quantum theory through the process of measurement. The whole universe is a quantum system, evolving according to the Schrödinger equation, with us embedded inside it, observing it, being part of it. That quotes quantum mechanics. Strange, precise, counterintuitive, and absolutely fundamental to how nature works.